so 8.4, that video that you watched, was talking about the when you have an improper bound that's at the ends of your interval. So either you've got an infinite end or you're coming up to a point that's not defined in the interval, okay? We want to talk about what if your discontinuity happens in the middle of your integral. So like, what if your integral looks fine? It looks like it's from 1 to 4, but that area space crosses over an asymptote. Then we're going to use the same idea of an improper integral within the bounds of an integral to solve it. So we're using limits again and just a replacement of those values. Okay, so we've talked about the 8.4a, discontinuous at an endpoint. That was that lesson, where the end of an interval is either plus or minus infinity or otherwise undefined. So for example, maybe it was a tangent interval that you were trying to do, except it was ending at an asymptote. Okay, so that was 8.4a. So 8.4b, both endpoints are fine. But a discontinuity occurs between them. So a different kind of improper integral, but the process of getting around that is still fine. Is going to be the same. If these are multiple choice, a lot of times you can get right to the answer without showing a ton of work. But if these are FRQs, they're wanting the rigor of you showing the limit definition properly in that process to get all the way to the right antiderivative. All right, so 1 and 2 right here on the pink slide, that was 8.4a. Okay, that was when you're replacing either the upper or the lower bound. Number 3 is 8.4b. This is where we need to separate the integrals at a point of discontinuity. So, you know, Alex, you saw that earlier problem. You separated it at 0, which is actually a point of continuity, and you had two things on either side, right? You had a negative infinity and a positive infinity, but then you separated it at 0. Okay, and this situation, we're going to separate it at an undefined point, and we're going to put the minus stuff all on one side. So if we're separating it at the letter C, we're going to put all of C minus on one side of an integral, and we're going to put all of C plus on the other side of an integral. So we'll always end up with two pieces, two different integrals to find. All right, so let's start with the functions defined as 1 over the radical of x. Think about the domain of that function. So Kaylin, as you're thinking about that, what numbers wouldn't be allowable in that function? Okay, what other numbers wouldn't be allowable? Because, why wouldn't negative numbers be allowed?
Because square root.
Can't square root a negative number, okay? Is there any other numbers that wouldn't be allowed?
0.
Why?
So that would be undefined. 1 over 0 is undefined.
Okay, so it's not the square root that's the problem for 0. The negatives are a problem for a square root, but 0 is a problem just for the denominator in itself. All right, so our domain is that all x's must be greater than 0. The problem is, okay, well, before let's start, so then that would make a problem like this, the one I put in blue. This one would be okay. The reason it would be okay is because the bounds stay within the domain. The bounds are from 1 to 2. The domain says everything, all bounds have to be positive. Therefore, that one would be fine. The problem with the one we're dealing with right now is that the domain says you can't include 0, but our integral is trying to include 0. So then we replace that lower bound. We say, okay, we're going to cheat the system here. And we're going to go from a to 2. It's like, fine, I'm not going to go from 0. I'm going to go from a. But a is going to be really close to 0. And on which side of 0 will a be? A land. It'll be on the positive side of 0. So it's like we're just thumbing our nose at the system and saying, fine, I'm not going to use 0. You can't make me use 0, but you can't stop me from using a, and my a is approaching 0. So it's just literally a legal way, a loophole to get around the system. And then if you're okay, I'm going to switch this to x to the negative 1/2 because that is always my preferred way to do my antiderivative. So then we're going to proceed with the antiderivative, which would become x to the positive 1/2 times 2 plus c, going from a to 2. And then when our bounds get dropped in, we're going to have 2 rad 2. And then minus, and then the limit would be on the second half of it because that's when we're plugging in a. So then it would be 2 rad a. Is it legal for me to plug in 0 plus into that? Sure, I can plug in 0 plus into that. There's no problem with me doing that. That would give me 0. And so I just get 2 rad 2 is my answer. Okay, again, so that represents the area, even though we're starting close to 0 and 0 is not part of the domain, you can still find the area trapped between this curve and the x-axis, even though 0 is not part of the domain. Any questions about that one? Okay, Alex, you all right? You feel okay? Okay. Okay, so here we go on this one. All right. Jonathan, as you think about this one, what is the domain for this function?
All the numbers except for x equals 2.
Okay, so in other words, x can't be equal to 2. You're like, well, shoot, one of my bounds is 2. Okay, there's no problem. You won't let me use 2. I'm not going to use 2. I'm going to use b. But b is going to approach 2. It's just not going to be 2. And which side of 2, Juliet, are we approaching in this case? If we're going from 1 to 2.
From the left side?
Yeah, yep, so a little bit smaller than 2. So again, it's just saying, I'm not going to use 2. I'm just going to use something a tiny bit less than 2. And so we've got 1 over x minus 2 dx. All right, so that antiderivative is the natural log. Here is where your practice, your discipline, forgot to write my limit. Your discipline of using absolute values is going to be really crucial. All right, the natural log of the absolute value of x minus 2 plus c, going from 1 to b. And so now I'm going to plug b in. So I'll have my limit as b approaches 2 minus of the natural log of the absolute value of b minus 2 minus, and then I don't need limits anymore because I'm plugging in the number 1, the natural log of the absolute value of 1 minus 2. Both of these, if you didn't have the absolute values, both of them would give you negative natural logs, which again is not part of the domain of a natural log. That's why the absolute values are so important. So we end up with the natural log of the absolute value of 0 minus, when we plug in 2 minus and we subtract, minus the natural log of negative 1. absolute value. So we have both of those are negative numbers. 0 minus is a negative number. -1 is a negative number. But both of them were protected because we have the absolute value on there. So this is the same as the natural log of 0 plus. The absolute value takes the negative number and makes it positive, minus the natural log of 1. And for what we know about natural log graphs, both of those have something we can learn from a natural log graph. We know from the graph of a natural log that the natural log of 1 is 0. What do we know about the graph of a natural log when you're just barely to the right side of 0? Can you picture the natural log graph? It is. It's negative infinity. Because of the way the asymptote is shaped, that natural log graph comes up from negative infinity, then crosses at 1, and then heads off. So we have negative infinity minus 0. So the answer to this integral is negative infinity. What that means in terms of area is that it's not possible. It was possible last time. I could capture a finite amount of area, it was 2 rad 2, underneath that graph. For this one, it's not possible for me to capture a finite amount of area under this graph. The area itself is going to be infinite in a negative sense. So it's just a lot of negative area underneath the x-axis. Okay, any questions? All right, Rain. Okay, thinking about this one. What are our domain restrictions? Yep, can't use 1. So x not equal to 1. The problem is that 1 is right smack dab in the middle of the integral from 0 to 2. So we need to separate this integral into 2 pieces. So we'll have an integral that goes from 0 to 1 minus. And I'm going to use negative powers. Negative 2/3 dx. And then we're going to have 1 plus to 2, x minus 1 to the negative 2/3. So we just have to chop our integral in half. It doesn't always going to be right exactly halfway. It may be depending on the size of your integral, but we're just going to split it at 1. So this is us saying, well, fine, we won't use 1. We'll skip right over 1. We'll get as close to 1 as we can from the left side, and we'll skip right over it, and then we'll pick it up on the other side. So then using limits, you would replace, and you'd say, okay, I want to go, this one is going to be the b limit, because it's the upper. So I'll go from 0 to b of x minus 1 to the negative 2/3. And the other one will be the a limit. So a approaching 1 from the right-hand side, and that's going to go from a to 2 of x minus 1 to the negative 2/3. Sometimes this lesson feels silly because it's like a legal way to get around, to skirt the issue of a domain problem. All right, so then we're just going to show our antiderivatives. So that would be x minus 1 to the positive 1/3 times 3, plus the constant c, going from 0 to b. And then the other limit, approaching 1 from the right, same antiderivative, going from a to 2. All right, and then we drop in our values. So we'll have 3 times 1 minus minus 1 to the 1/3. Okay, so I just plugged in the b, and the upper limit of b was 1 minus. Minus 3 times 0 minus 1 to the 1/3. So I've just plugged in my upper and lower bounds. And then I'll add to that 3 times 2 minus 1 to the 1/3 minus 3 times 1 plus minus 1 to the 1/3. couple of those turn out to be versions of 0. So the first set of parentheses is 0 minus, and the last set of parentheses is 0 plus. So both of those are cube roots, and it is possible, it is legal to cube root a negative number. And a cube root, as long as you're not applying that cube root, so the cube root of that value is going to be 0. So we'll have 0 minus 3 times, and then the cube root of a negative number is still a negative number, so that's 0 minus 3 times negative 1. And then plus 3 times 1, and then minus 0 again at the end. So we end up with 6. Again, so what this means visually is even though we have an asymptote, we have a finite amount of area captured in this little section. Okay, if you took the drawing and you made it and you shaded in your area, you got 6 units of area trapped even though there's an asymptote in the middle of this. Excuse me, a cusp in the middle of this. Okay, last one. Finding a volume. So now we just got to dig back and remember how to find the volume when we rotate. We haven't done this since about end of October, beginning of November. Okay, to find the volume, rotating this around the x-axis. So let me try and draw my best reflection here. Okay, something like that. So we're rotating this around the x-axis, and it looks like, I don't know what, that reminds me of a little bit like a teardrop, kind of. But we've got this rotated here. A beat. I don't know. All right, do you remember how to set up the rotation around something? What shapes would be formed if we actually sliced this thing? Circles, little discs, right? So we want, what's the area of every disc that's formed? Because they're circles, the area is pi r squared. So we're integrating pi r squared. We integrate the shape of the area. And so we want to set up an integral that's going to be pi times the radius squared according to the x-axis. That's what we want. But look at what the bounds are. The bounds we're given include for us x included, but infinity not included. And we can't do a math 9 because infinity is a bound and your calculator can't do it. All right, so here I gave you some area, space to write this in. So our volume is going to go from 0 to infinity of pi times the radius squared, and the radius was x e to the negative x, quantity squared dx. So that's our setup. So I would pull the pi out altogether. I'd set up the limit as a b approaches infinity of the integral from 0 to b. And then when you square everything, you're going to get x squared on top, and you're going to get e to the 2x on the bottom. Or you can also write it, if you don't like the denominator way, you can leave it as, in fact, I think I like it better the other way. I like it x squared e to the negative 2x dx. I think I like it better this way because I'm going to do tabular to this. Because here I see a product which would take me at least 2 integration by parts, but I can do it faster with tabular. So I'll set this up. All right, so Kaylin, on tabular, what would you put on the u side of the column using the Lippitt test?
X squared.
Yeah, I would too. So then you're going to have x squared, and then you're going to have 2x, and then you're going to have 2, and then you're going to have 0, which leaves e to the negative 2x to be on your opposite side. So my antiderivative would be negative ½ e to the negative 2x. My antiderivative of that would be positive 1/4 e to the negative 2x. And my antiderivative after that would be negative 1/8 e to the negative 2x. And then we'll combine diagonally, and we'll change the sign of the second one. So we're going to pi, again, is completely outside of that. And then the limit of the antiderivative this time, and the antiderivative is going to be negative 1/2 x squared e to the negative 2x minus positive 1/2 x e to the negative 2x. And then looks like minus 1/4 e to the negative 2x plus the constant c going from 0 to b. And then you drop in your bounds and evaluate your limits. I would factor this, I think, first for me personally. I think the factoring, what would you pull out if you guys were looking at that? E to the negative 2x for sure. What else? I'd pull up the negative 1/2. I don't think I can pull the x out of the whole thing, but I could pull a negative 1/2 out. And that just makes it a little cleaner visually.